Hey, welcome back to Feynman Physics. In this video, we're gonna do example 6, which features a Feynman diagram, and we will need to analyze this Feynman diagram. I believe this question was taken from an IB. This is an IB question, so it's going to be really relevant. And it seems like our Feynman diagram is drawn for us, and we just need to fill out some of the blanks, which is really helpful since there is probably no way, very hard for us to figure out exactly what is happening with everything here. And we also don't know the composition of each of these particles, which usually a question needs to provide for us as well. So we have A, B, C, D. Let's get started. All right, so it's the above equation here is the decay. We have a kaon gets decayed into a bunch of different mesons. So yeah, we have a meson to start with, a kaon here as an anti-up and a strange quark, and it actually looks like several other particles. Yeah, so several other pions are being produced here as well. So let's start off with question A. Explain what is meant by an exchange particle. Sometimes an IB question might call it a virtual particle, and that's just to say that it's just a way for us to model the fundamental forces using a particle as a mediator. And this is exactly what it is. It's a particle that mediates a fundamental force with an interaction between particles. So it's a particle that mediates one of the fundamental forces between interacting particles. Particles, all about particles. So next up we have B here, which is identify X, okay? Okay, so we have a bit of unknowns. We have X, we have Y, and I believe that is it. So we want to first identify what X is. You might think that, oh, it looks like a gluon because of the wiggly lines. The curling lines, but we always want to make sure. So always good to check what you have and what you end up with. The easiest thing to check is always the charge. We have a strangeness quark here, which has a charge of -1/3. And for a down quark, this one over here is a -1/3. An anti-up is going to be -2/3. And which means that this X particle is going to have a negative charge. It is likely going to be a W- boson, but we can just check that with the other junction over here. And since at this junction we're producing up quark, which is a +2/3, we have -1/3, and minus a -1 charge is going to give us +2/3. So yes, both junctions check out with a W- boson. So that's what that's going to be. Next up, we want to determine the electric charge of Y. Okay, so I think this might be a little bit trickier because well, first of all, we do know that this up quark continues down over here. So this is an up quark, and it doesn't seem, we are not very sure exactly what there could be many possibilities. So there's a bunch of exchange particles that don't have a net charge. So let's see what we got left over here. So here we have a down quark leaving this junction, and we don't know what this one here is. But we could figure that out by the fact that this is a plus pion, this is a negative pion, and usually for the antiparticle, it's going to have the opposite particles that make them up. So, for example, this negative pion is composed of an anti-up and a down quark. For the positive, or the antiparticle, is going to have the opposite. It's going to have a regular up quark and an anti-down particle. So it looks like this, okay? So if we double check the charges, this is going to be exactly opposite in charge, which means it produces a pair of quarks. This is a -1/3, this is a +1/3. So this Y would have a charge of 0. Oh, that's all we need to do. We don't even need to determine the exchange particle. So we know that the extra charge of Y has to be 0, okay? We don't even need to determine whether or not it's a strong force or if it's a weak force or an exchange. So in my guess is that it's mediating a strong force. It looks like yeah, it looks like here we got an elongation of a gluon tube, which then produces a pair of quarks. So that's kind of my guess of what's happening here. So I'm guessing this is a gluon, but we're not told what exchange particle it is, so we can just say that it has a charge of 0. And that's how we determined it, okay, using the two junctions. D, calculate the charge and strangeness in the decay of the K minus. So in all of our products, there are no strange quarks. There is only one strange quark in the reactants. So we want to find the change. So change always means, oh, let's just say change. I'm so sorry, it's not charge. So that usually what we want to find change is final minus initial, okay? And in our case, we know final is 0, it has a strangeness of 0. And in our initial state, there is one strange quark. One strange quark will have a strangeness of -1. So if we take a look at this overall change, the overall change is going to be +1 in strangeness, means it gains a strangeness number in this process. Okay, so that is it. We just have to calculate it, so we don't have to explain anything. There we go. That's the question number 6. Woof! So, lots of deductive work, and I hope you enjoy the deductive work as well. It feels like a puzzle solve. It kind of feels like a puzzle, so that's kind of what these reactions are like. So, hopefully you enjoy that as well, and I wish you the best of luck. Fan Mama Physics, signing out!